So last class we talked about elastic collisions. Okay, that's where we came up with that formula that we were using. Again, that's where there's no energy loss. Okay, no energy loss. So for today's class, we're going to look at when there is some energy loss. So for example, when two objects collide, and when they collide, they happen to stick together. They can only stick together from heat. Heat is energy loss. That's a simple example to think about always. Okay, so it's an object that gets somehow like stuck to the other object, and we lose some sort of energy there. Okay, so today what we're going to start off with, we're going to look at an example. The best example for this to actually use is going to come in a second. We're going to talk about a ballistic pendulum. Okay? A ballistic pendulum. And I'll explain exactly what it is. It's actually pretty cool. You use a bullet and a pendulum, correct?
Oh.
So, let's start with an example first. Okay, with the first example of this. We're told that there are two railroad cars. Okay, two railroad cars. So we have railroad car 1, or car A, traveling east, collides with railroad car B. Okay, so again, car A collides with car B. They stick together, so they lock in. How do they lock in?
They're trained.
They're trained, so like you know how trains have the joints between them? The pins clip in.
The what?
There's a joint between the train that they clip into. Okay, so again, this object clips in with this object. Let's say that this object has a mass of 1,000 kilograms. This object is a mass of 2,500 kilograms. So we're told both masses here. We're told both masses. We're also told that this one starts with a speed, okay, to the right. It starts with a speed of, let's say, 50 meters per second. 50 meters per second. Now,
at this time, all students should be in lunch? Or at what period?
The collision causes these cars to stick together, so afterward we lump their masses. That's what we talked about last time. So our goal here is this. Our goal is to figure out what the velocity is. Again, this one, sorry, this is at rest. I should have put that at the top. The velocity of the combined trains afterward, and then how much energy was used to actually clip them in. Because there is energy loss there, okay? Again, we're going to find or figure out the combined velocity of the train system after the collision, and then we're going to say to ourselves, how much energy did we actually use to clip them together? Because we have to use energy. You can't just have it on its own. Okay, you can't lift up a lever, put something under it, and put the pin over it. That's really what's happening there. One of the levers lifts up, one of them goes below, and they clip in together. You need energy to do that. So where is that energy coming from? That's what we're going to look at today. So the first thing we want to do is go back to our kinematic equations. Okay, start. We have momentum before equals momentum after. This kind of a problem is a little easy. We did this one already, if you remember, because this is at rest, and afterward they're together. So in the beginning, we have the mass of object A times its velocity initially. Again, this is in the beginning, this is moving. In the beginning, car B is at rest, so I don't have to worry about it. So in the beginning, there's nothing from car B. I can put a 0 or just leave it blank there. Afterward, they're stuck together. So what's the total mass going to be, numerically wise?
3,500.
Good, and you got that by adding them, right? So that's where this MA plus MB comes from. Again, because we are adding them. Then, we know that they have the same velocity, because again, if this car is moving, it slams into the front car, and then they're stuck together. So now they have to be moving in tandem. So the velocities are the same. So I can just simply put VF here. I don't need to put VAF or VBF, because they're together. It's the system of cars. Now, think about this. We know MA, we know VIA, we know the M's here, we can solve for VF. What do I get when I solve for VF? Oops. Get off the screen. When I solve for it here, I'm going to look at this. I'm going to have 1,000 here from the first one. A speed of 50 meters per second, equaling 3,500 VF. Again, if you want to solve analytically, I encourage you to. I'm just showing numbers. I'm going to go back and forth sometimes. So you could divide by MA plus MB on this side. We're going to use that in our lab next week when we do a lab. We're going to talk about how we divide by this and use that in the equation. Keep that in mind. Solving for VF, you're going to get, looks like
14.28.
what do you get, sorry? 14.28. Y is what? Before and after. Look at our original equation. Remember? Momentum before equals momentum after. So the momentum before the collision is only car A. It's moving. It hits it. They combine together, and now they're moving together. If they're moving together after the collision, we call that the final velocity. And so this is before the collision, after the collision. So when they solve for VF, as Starr told us, we have 14.28 meters per second. Okay, agree with that number? Oh, there's a check, I hope?
Yeah.
Now, the question is this. That's great. We got our velocity afterwards. But how much energy was used? So let's look at energy. And we know from inelastic, we say energy before is equal to the energy after plus some Q. Remember we talked about how this is a dissipated energy? It's energy that goes off into the atmosphere. Okay? So an easy way to think about it is like radiation and stuff, that kind of energy or thermal energy. Your body is constantly giving off energy. Why do you think sometimes you come in here and the room is warm? Because a lot of people have been here and moving around. So you're constantly using energy. Your body's giving off this heat. So it could be thermal. It could be any type of energy. There's many different types. But we're just going to say it's some sort of energy here. So if we can figure out the energy of the system in the beginning, what kind of energy is in the beginning if an object is moving? Kinetic. Is there potential at all? No. Again, moving on flat land, there's no change in potential. So the energy in the beginning is all going to be kinetic. The energy at the end is still moving, is all kinetic. Well, there's not going to be the same number on both sides. What takes account for that is this Q. Okay, again, the energy of the one car at a high speed, the energy of the combination of the cars at a lower speed is not going to be the same here. Okay? So in the beginning, we have 1/2 MA, because the mass of car A is moving. Remember, in the beginning, car B is not moving. Go back to your diagram, look at your diagram. Car B is not moving in the beginning. So we have 1/2 MA VAI squared. Again, 1/2 MB squared. Same as last chapter, but the subscripts are just indicating that it's car A in the beginning. Now, car B is not moving in the beginning, so I don't need anything. So then put equals. Afterward, it's 1/2. Now, what's the mass going to be? And the sum of the both. Good. 3,500, or simply MA plus MB. Remember, afterward they collide, so the mass is like one giant mass. And what's their velocity after? Well, we just figured it out. That's VF. And it's VF, very good, squared. Now, these are not going to equal each other. So there's going to be something missing over here. That's the Q. Okay, that's the Q that we're going to be talking about. That's the heat loss. So come out with a number here. You're going to plug in. We're going to plug in a number here. We're going to have 1/2 the mass of the first car, which was 1,000, times the velocity of the first car, squared. Second, we're going to have 1/2 3,500 times its velocity, 14.28 squared. What do you get on the left side here?
25,000.
25,000? Divided by 2 should be.
1,000 times 50 divided by 2.
50 squared is 2,500. 2,500 times 1,000 divided by 2. Again, guys, square 50 first. Thank you. That's exactly okay. That's very good. Again, take a look at your numbers. You know it's going to be 125. 50 squared is 25, really, or 2,500. Still got to have a 25. Half of 25 is 12.5. So you're going to have this number in here somewhere. Now, on this side, it's key to see what we get here. What do I get over here?
Number.
Can you give me the number or no?
Christian.
356, 857.
Do that by pencil.
Okay, approximately. I'm rounding it. Okay. Now, where is the energy? Look at the difference. Almost 900,000. Almost 900,000 joules are gone. Everybody see that?
Thank you.
So the energy in the beginning is all here. it lost almost 3/4 of its energy. And I want to make sure we focus on that. Put a plus Q here to show that that's where we're missing the energy. Subtract the 356 from both sides to find how much energy was lost. Again, there's the plus Q here, really, because there's energy loss. Subtract this number from 12, 5, 0, 0, 0, 0.
You get 892,143.
Yep.
Okay, now 140.
193.
19.
193. No.
No, 800. Change the 2 to that. Okay, that's a little thing.
Okay, so let's think about this for a quick second. In the beginning of the problem, we had almost 1 million joules of energy. We had 1.25 million joules of energy. In the end of the problem, we only had 300,000 joules of energy. So we lost about 900,000 joules of energy there. Now, let's think about this logically and think about what heat loss does to us. You start with this much energy. You lost this much. So you have this much left. What is 3 out of 12? 1/4. Let's look at this. You have 3 left, really. This is like 3 out of 12. Look at the numbers here. Look at that 3 and line that up with the 12, approximately. It's closer to 3.5. So we have about 1/4 of the energy left. 3 out of 12 is about 1/4. So we lost almost 3/4 of our energy. 3/4 of the energy was lost in the trains just to clip them together. Does that make sense here? Again, you have 300,000 left. You started with about 1,200,000, which is 1.2 million. So if you have 300,000 out of 1,200,000, we're really looking at like 3 out of 12. So we have 1/4 of our energy left. So this energy loss represents 3/4 of the energy that we had to start. We lost a lot of our energy just due to linking the trains together. Okay, just due to linking them together.
Is it less good?
If the first train was moving,
If both trains are moving, would it be less?
depends on which direction and stuff. Are they moving together?
Yes.
So this one's moving, this one's catching up.
Yes.
Depends on how much is moving. We could try it. All you would change, I'm not going to do it, but all you could change is this. This would not be 0 because it's moving in the beginning, and this number would probably be higher. It would not be something, well, it will be higher. The answer will definitely be higher. So you're changing this value, which increases this value, which changes your energy in the beginning. Because now in the beginning you have 2 forms of energy, MA and MD. But this number will go up. Which one goes up by more, and then you're squaring that number. So keep in fact that you're increasing at a square rate.
My handwriting sucks. I have a question. How do you know when you use elastic and inelastic? I know you were
The
saying
problem
that-
says it. The problem
Say
tells
it?
it, of
Yeah,
course.
because I was going to ask because
In
like,
your notes, guys, write that down, please. If it says elastic, there's no energy loss, so no Q involved.
I was wondering because like, I mean, we could always make a perfect situation.
Absolutely. Absolutely, he's right. Again, we can assume things to be elastic sometimes, okay? But the problems that you're going to be studying, you're going to work on, will tell you one or the other. Okay? So let's go to the main problem from today. And again, guys, this is recorded, so if you had other stuff to do for a second, you just came in, make sure you watch it. The second problem is this. And I find this to be kind of amazing that somebody thought about this, to be honest. Imagine you have a wooden block suspended from a cable. And it's got to be wooden, or something that can be shot into. And imagine now, if somebody stood over here, and what you're trying to do is measure the speed of something. If you fire an object, you can think of a bullet to be easiest, but if you fire any object, and it hits this, and impedes it, embeds itself inside of it. So the bullet gets shot, it's moving this way, it hits the wood, and it gets stuck in the wood. The height that it moves it can tell you the velocity it was at. Okay? That's how ballistics work.
Velocity of the bullet?
Again, the bullet is fired. It hits the wood with a certain velocity. Based on that velocity, this will move. It'll like slide up, right? Imagine something's being suspended and you hit it. It moves up, right? If you hit it faster, it moves further. So the height at which it moves will tell you the velocity at which it hit this. It's all from inelastic collisions. It's like the Newton's cradle. Same idea as Newton's cradle. Okay? The height at which it will move really comes from how high you started this up, which then translates to the velocity at the bottom. So what we're going to do here is we're going to use our idea of kinetic energy and potential energy, and then also we're going to look at ballistics or inelastic equations.
Do we have to worry about the material that's being shot?
No, you don't. The material doesn't matter, but the mass of the objects does matter. Okay? So, let's talk about this problem first. In the beginning of the problem, this is where energy and momentum are going to come in together. In the beginning of the problem, we have the mass of the bullet, we have the velocity of the bullet. Okay? I'm calling it B for bullet, not B for object A and object B. This has a mass, we'll say it's the mass of the wood. Okay, the mass of the wood. So B is bullet in this problem, W is wood. Many of you guys don't write that down. Okay, if you don't write it down, it's fine, but please don't forget later in the problem, because it gets a little bit confusing. So W is wood, B is bullet.
It's a solid piece of wood, right?
It's a solid piece of wood, yes. In the beginning of this, the velocity, it could be hollow. It could be hollow.
It could be hollow.
The W for wood, okay? B is for bullet in this problem. The velocity of the wood in the beginning is 0, because it's not moving. Then when the bullet hits the wood, it starts to move. Okay? It starts to move. Now, the question becomes this. Thinking about only energy and only momentum, can we find a way to figure out, based on the height that it travels up, what the speed or the velocity of the bullet was when it hit? Okay, what is that velocity? So, we want to think to ourselves for a second. In the beginning, all we have is this, mass and velocity. Afterward, we have mass and velocity that are clumped together, so as a final. So when we start looking at our equations here, okay, we have the total before, so let's start with momentum. Momentum before is equal to momentum after. Okay, momentum before is equal to momentum after. Now, beforehand, we have the mass of the bullet times the velocity of the bullet. Not given. We're doing everything with variables here. Guys, we're going to do everything with variables for a second. Okay? So, all analytical solution. Afterward, we have the bullet and we have the wood together. Okay, we have the momentum of the bullet and the momentum of the wood together times the velocity of them together. Remember, same equation as before. The bullet is moving by itself. It hits the wood. They combine themselves. Okay, they become one. This is that value right here, and they have a velocity together.
I thought it was mass.
What was mass?
MQ.
M is mass.
That momentum.
Momentum before equals momentum after. This is mass times velocity, which is momentum. P represents momentum. Lowercase p is always momentum. M is mass, yes. Now, that's our equation for momentum that we have. From energy, this is the tough part. We have to think about this. If we look at the energy of the block right as it hits it, and then look at the energy it gains as it goes up. So again, when this bullet hits the block is going to start to move. When an object is moving, what kind of energy does it have? Kinetic. Now, watch my hand. This is the object. It moves up here. It stops, and then it starts to come back down, right? Think about a pendulum. Comes up and then back down. When it gets to the top, what energy is it? Only potential. Because again, it started to move. It stops. When it stops, there's no kinetic. It's gained height. So it's potential up here. So what we're going to look at right now is the energy balance between this point in time, stage 1, and when the box is up here, stage 2. We are not looking at the energy in the beginning here. Does everybody see that? That's the difference in this problem. Again, we are not comparing the energy here and looking for the energy loss. We're not looking for Q in this problem. Okay? We are saying that this block has a certain amount of energy. When it moves up here, it has the same amount of energy. It's only potential. So we can write a relationship between potential here and kinetic here by setting them equal due to conservation of energy. Again, yes, we lost energy. We had more energy in the beginning than we're going to have right here. But I'm not caring about that Q anymore. I'm looking at the energy here and the energy here, which should be the same. Think about a pendulum. It's the same energy the whole time. That's how Newton's cradle works. If it stops, it's because of friction. But we're not looking at friction here. We were only looking earlier at the Q, but we're not looking at Q. So again, kinetic in stage 1, potential in stage 2 need to be set equal. Kenneth?
We have the height of the box, right?
That's what we're going to figure out next? Yep.
No, because doesn't the ceiling play a role in the height? Because I mean, like if
Sure. Yes. I know exactly what you're going to say. Absolutely right. So, in the beginning here, the energy before, it's the wood and the bullet together. Again, the energy before, if you want to write a little note in case you're forgetting, this is kinetic in the beginning. The minute the bullet hits the wood, it starts to move, so it's kinetic energy. Then the wood and the bullet move up to a certain height, giving it potential energy at the end. Okay, potential energy. Now remember, the bullet and the wood are together, so we lump their masses together. Now, at the end of the problem, the bullet and the wood are still together, and we would normally write mgh or mgy. But instead of m, I'm going to put mw again, plus mb again. Again, because the bullet is still part of the wood now. So this is stage 1, when the bullet hits the wood, and once the pendulum comes to the top of its path, it's stage 2. That's what this is over here. So this is this times g times h, or y. Either variable is fine. Use whatever you would like to. I've used y before or h. So, if we can figure out, this is what the cool part is. If we can figure out a way to solve, here, we can determine the velocity of the bullet just by looking at how far the pendulum moves up. So we'll see in our answer will only be a function of h. Okay, so based on the height, we can determine that velocity. So what I want to do now is look at this. Clearly, these m's are the same, aren't they? So what should I do to them? Cross them out, please. Okay, cross those out. And we're good. That's exactly what we're going to do. That's exactly right, Karen. Again, we're going to solve for one of our missing variables over here and move it over here. Okay, solving for one of them over here, and we're going to move it over here. Sorry.
So how come the last time you couldn't cancel?
How come you couldn't cancel on m's?
Yeah, elastic. Like you told us some problems you can't cancel out the m's.
Because the m's were different. Like you had like MA over here, MB over here, then MA plus. But these are the exact same values.
The bullet.
The bullet and wood combination is on both sides. Isn't that what those mass are? So it's like having M here and M here. M's drop off.
Wasn't it the pole?
because they're multiplying.
Isn't it what? The billiards ball, they canceled because they were the same mass. The billiards balls were identical. And in the next example, the masses were different, and they couldn't cancel. But here, this is the same as this. Those are the exact same masses. Okay? Because they're sums of the same numbers. So, reducing this, please write now here. So, write down the next equation that results from canceling the masses. Now, the goal of this problem was to find the velocity of the bullet. We are looking for this velocity right here. Again, the problem is saying find the muzzle velocity. The muzzle velocity is the velocity of the bullet as it leaves the gun. Okay, the muzzle velocity. So we are trying to find dBi. Now, if I want to find dBi, I can see that there's a VF here and there's a VF over here. Everybody see that? There's a VF in two spots. So that's going to be my linking variable in this problem. Remember how t was our linking variable for projectile motion between the x and the y coordinates? T was always the linking variable. Here's my linking variable. Now, my recommendation for you guys is this. Solve for VF here and move it over here instead of here and here. Because if you solve for VF, then you're going to need to square it and it's going to get messy. Here we can just simply move the 2 up and take the radical of both sides. So multiply both sides by 2 to get rid of the 1/2. The 1/2 and the 2 cancel. So I'm left with 2gh now. So I have VF squared equals 2gh. And I say VF equals radical 2gh. Well, that should be very familiar. We use this equation when an object was dropped from a cliff to the bottom. It came up over and over again. So we're going to take this plug it in up there. Again, plug in that expression for VF. You get MB VBI equals MB plus MW times radical 2GH. Again, our linking variable is VF. We solved for VF squared. We took the square root. We got that answer. God bless you. We plugged it in for VF. The question, though, says find the muzzle velocity. So we got to get rid of that mass. So simply divide by MB now. Okay? Now, the problem is this. Not the problem, but the situation is that we have to use an experiment. The experiment will tell us H. We observe that. Again, so by our observations, we can measure the mass of the bullet easily. Agreed? You can measure the mass of the wood easily. You can measure the height change, and you know G. So without even using a speedometer, you can find the velocity of the bullet when it exited the gun. Okay? With no work whatsoever when it comes to kinematics here. It's all energy. All energy. Kinematics would tell us, I fire a bullet from a gun, somebody stands there with a radar gun and does this, right? Well, you don't have a radar gun. This works just as well. It gets the exact answer every time. So imagine a baseball player takes a baseball and throws it into a wooden block. But let's say for this example, the wooden block is open on this end and there's cushioning in the inside. So when the ball hits inside, it stays in there. Imagine there's a lot of cushioning and there's an opening. And you've got like Nolan Ryan, who can hit it perfectly through that opening. He throws the ball, it goes perfectly through the opening, the wooden block slides up. It's the exact same thing as a bullet. So before they had things like radar guns, how do you think they measured velocity of objects? This is the way they did this. Okay, so this is a very old school method to do it, but this value here, this entire quantity, which we bring down right there, is the exact velocity of the bullet when it leaves the gun, or the velocity of the baseball when the pitcher throws it, when he releases it, or she releases it. Okay? Again, I know it's a tough problem because it's all variables, but you can see that we can measure every one of these quantities. We know G, we can measure H, we know M's, so we're good to go there. Next problem.
But you just saw that.
It has to be at rest. This problem works when the wooden block is at rest. Absolutely. And you would have V with the velocity of that block, which would be another.
It's really easy. I'm just, but I'm not thinking.
Guys, you probably have the same question. Let's please listen to Bridget.
Like you say, but you got velocity, find this because it's going to be the same velocity.
Oh, very good point. Let's take a look at this. And I didn't even mention that. In momentum, initial momentum occurred, and please be careful, listen to this. This is very important. Initial momentum occurred here. Final momentum occurred here from our equation. But when we did energy, we called this the initial, and we called this the final. So the final velocity of momentum is the same as the initial velocity of the second part. Remember the other day we did a piecewise function, I said? And I used the example and I said, the final velocity at the end of this stage is like the initial velocity at the next stage. So, this is like stage 1, this would be the pre-stage. So this is like beforehand. The velocity of the bullet here, okay, is the initial velocity. This is the final velocity of the bullet in mass of this situation. But now, once I'm done with momentum, I'm now looking from here to here. Now, since this is now my beginning, the velocity of the end of this is the velocity of the beginning of this. Okay? So imagine of like, simple example, something like a soccer ball. I kick a soccer ball to somebody, it has a velocity. When Edgar or somebody goes to return the ball, I just saw Edgar, he kicks it back. The initial velocity of the ball is the final velocity of my kick. So I kick the ball, because this is a very confusing thing to think about. I kick the ball here with some velocity initially. It might slow down by the time it gets to the other person. It has a final velocity. Now that person goes to kick it back to me. Well, this final velocity that I had this way is like the initial velocity the ball had for that. If a ball's coming at you, it's got velocity. It's the final velocity of my kick. Well, then when you kick it back, that's your initial velocity, and then you'll have another final velocity. So this final velocity is really the initial velocity of this ball. And this would be a new final velocity. So it's going back and forth, guys. Okay?
But isn't the person kicking a ball?
Sure. So this is going to have a different final velocity. But the final velocity of your kick is the same as the initial velocity of their kick. Once they kick it, Karen, then it has a final velocity. So this is before they kick it back to you, really. Then they kick it, and it's got a new velocity. That's based on the new force. Okay? How do we know to put which one?
On this side.
Right here?
How do you know for 1/2?
We said the energy before was kinetic because it hit the wooden block and the ball in the wood started to move. Then it changed into potential energy as it rose up. Remember the skateboarder?
Yeah.
Kinetic energy at the bottom, potential energy up top. Okay? So kinetic and then potential up top and then solid. Again, that's kinetic there because they're together. That's potential because they're together. All right, I want to try a problem that can show this.
It's always twisted. I like it that way. Oh, really? It is? Oh, wow, you're right.
Look how big it
No, it's a binomial. You'd be like saying x plus 2, and that would be an x down there. The x's don't cancel. You would have to divide it everything. Okay, here's a great problem for us. Everybody has this formula written down right here? Using this formula, we're going to try and figure out the difference between velocities of two different objects. So, use that formula again. We're going to use that formula.
So that there
We have-
Sounds confusing.
We have two projectiles fired in a ballistic experiment, two of them.
Together.
One of them causes it to move up a height.
The other one causes
So two objects are fired, they're different objects. The first one causes the height change to be
well, that's good. You'll give us the height. You get the height.
2 centimeters. The second one causes the height to go up. Bridge, please listen. The first one causes the height to go up 2 centimeters. The second one causes it to go up 5 centimeters. First of all, which one is traveling faster?
The 2 centimeters.
The second one, hopefully. Again, think about the pendulum. If the pendulum moves further up, it means it hit it faster. So this will have a higher velocity. Now, we are also told that the masses are the same for everything. Okay? So the mass of the wooden object and the mass of the bullet is the same bullet, the exact same bullet, just fired in a different gun, we believe. Okay? So one can fire it faster than the other. Based on these two values alone, find out how many times faster this bullet was shot than this bullet. Okay? So, it seems like it's confusing because you only have two things, but we really have all those equations. So let's use our linking equation. So before we go back, let's write our equation here in the middle, and then we'll go back to the actual solution. Our equation from the last example told us the velocity of the bullet, or the object that was moving, not the stationary object, was the mass of the combination, okay, mass of the wood and the bullet, times square root 2gh, all over the mass of the bullet. Okay? This is one of those formulas where, like, you use it often enough, you'll get to memorize it. You don't have to, but it is one of those things you would write down maybe. Okay? You might want to write it down and put it on a note card. This is the velocity of the bullet as it leaves the gun. Now, clearly here's the problem. You don't have these values, you don't have this value, you've got G, you've got H, but we don't have these. But we are trying to figure out a ratio. How much faster will this one travel than this one? So in the end, we're going to divide them. So when we divide ratios, we're going to have this over something very similar. So you're going to see all the masses cancel. So let's go ahead and do that. The velocity on the left side, again, will be VB equals MB plus MW. We don't know that. We know square root 2gh. That's going to be 2 times 9.81. Again, 2 times 9.81 times the height. What should I make this height, though? Meters. Probably should do meters here, right? So we're standard. So just quickly convert to meters here. 0.2. Again, 2 spots. Sending means 2. So move it over 2 spots. So this is really 0.02 meters. This is really 0.05 meters. Just note that, please, because we're going to use those numbers. When you plug into the radical, we're going to do, again, 2 times the square root of, 2 times 9.81 times 0.02, all square rooted.
Doesn't really make a difference.
No, it doesn't. And you're going to notice that. We'll get to that. Just hold on for a second. It's one of our conclusion things. Good to note though. What do you guys get? Can somebody do that again? 2, 9.81 times 0.02, square root the whole thing. Times 0.02 is the height.
6 point. Oh.
Again, 2 times 9.81 times 0.02, square root.
0.6264.
That's after taking the square root, right?
Wow, all I do is that's
Okay. Now, I know it sounds weird right now because we don't have a lot of all our numbers here, but just bear with me. That's the first one. Again, 6264. For the second one, the velocity of bullet 2, okay, the velocity of bullet 2, it's called VB, it's the second bullet. We got again, that will be the same, of course, but what is it going to turn out to be? Instead of 0.02, use 0.05. 0.9 what?
9.
Thank you. Okay. So, here's what we look at. Focus on this. Here, we've got a number like 0.99. Here we've got a number like 0.6. Clearly this one's going faster. Is that agreed? This number is bigger than that number.
3 to 1.
The question says, find the ratio, or find how many times faster it goes. If you want to find how many times faster, you take this quantity and divide it by this quantity. So you're going to take this whole thing. So watch what I'm going to do now. And you don't have to actually show this. If you want to just watch, you'll see what happens. Take this whole thing here. If you want to find out how many times faster, the mass of the bullet plus the mass of the wood all over the mass of the bullet, 0.99. Take that whole thing divided by that whole thing. And all of your masses will drop off. And all you're really left with is the decimals over each other. That's all you're left with. This masses cancel with these guys. These cancel with these guys when you divide fractions. So pretty much this is like, it looks to me like 1.5. What's 0.99 over 624? Maybe 1.6, 1.5?
1.58.
What is it?
1.5.
1.6, approximately. Very good, thank you. So, this is what it tells me. It tells me that I don't know what the velocity is. It's just this number here. I don't know it. I don't know this velocity. But I do know that this one is moving faster than that one. And I can see how many times faster. Almost 1.5 times faster. Okay? Numerator, if you have a numerator in both of these, the numerators can cancel. This is just one of those things because you multiply by the reciprocal. You would really multiply this by the reciprocal of this, which would put this down below. And these would all switch spots. They would cancel. Okay? It's an algebra 2 thing. We did this last year. They all drop.
Is there a reason why you did that side divided by that side?
It says how many times faster. So we're looking at the faster bullet compared to the slower. If it said how many times slower, you would do it the other way and you would get about 2/3. Faster. Which one's faster, sorry? How many times faster? You take the bigger number over the smaller to see how many times faster. Do it the other way, you're going to get 0.6. 0.6 is a fraction. If you're running 0.6 times faster than me, you're actually running slower than me. Or vice versa. Okay? Now, here's the thing I want you to think about also. Look at the change in the height. Everybody take a look real quick. What was this height? About 5. This height was about 2. Okay? This was 5 to 2, the ratio. Reduce 5 to 2. Isn't that 2.5? 5 divided by 2? 2.5? Take the square root of 2.5. Everybody, take the square root of 2.5. What do you get? Because the h was under the square root. So we could have originally said, well, if this height is 5 and this height is 2, it's the ratio of 5 to 2. But since the h is under the square root, all you need to do next is take the square root of the whole thing. Does that make sense? Again, the h was the only thing that changed, and it changed under a radical. So you need to not take the ratio of 5 to 2, but the square root of 5 to 2, which is 1.58.
Oh, that one makes sense. That was a good
Let me say it again. It clicked somewhere. Let me go again. Here, this height went up by 5. This height went up to a height of 2. The ratio of the heights is 5 to 2. That doesn't tell me the ratio of the velocity, though, because the velocity is a function of the square root of the height. So if you take the square root of this, you don't get 2.5, you get 1.58, which was our answer that we got. Okay? 5 divided by 2, enter, square root of that, you'll get 1.58. Okay? Now, because, did we use the height? You have to use the height here to get this number and here to get this number. I'm just showing you another way you could have done it if you noticed it. Guys, this way, this is the way. If you were taking a class like AP Physics with an AP exam, and this kind of a problem came up, this is the problem where you would have to use this. If you did all that, look how much work that was. In the beginning of this problem, I could have just said to you, hey guys, what's 5 divided by 2? You could have said 2.5. Okay, take the square root. Well, that's the answer. Well, where does it all come from? This is where it comes from. This radical, the radical of h is where it comes from. But if you took an exam and you needed to save time, I would simply say 5 over 2, square root, that's your answer. You're done. Yeah, it was for a reason. It was.
So that the next thing each of seems so much.
If you're given 2 different heights, you can take the ratio of them and take the square root and go right to your answer. Sure, but you got to remember all that. You got to make sure you remember all that for the test. If you can remember that, it's fine. Not divided by 2, it's just the ratio. Whatever it is. If this was 6 and 1, 6 over 1, square root.
So we take the higher one and put it on top?
The ratio of the heights, square root of that will give you the ratio of the velocities. So if you want to write a conclusion, hold on one sec, Rachel, sorry.
Thank you. I can't believe the life's so boring. Boring life isn't bad.
That's what you really want to say here, sorry. So the velocity ratio, okay, the velocity ratio is really just the square root of the heights divided by each other. Okay? Again, the square root of the quotient of the heights. Ratio. I got the I in there. It's in there.
It just combined itself with.
There's
There's some thermal interaction there.
Okay. What I want you guys to do this weekend. Oh no. Yeah. I see you tomorrow, but tomorrow classes.
Yeah.
Classes are what tomorrow? Like 20 minutes? Exactly. So I'm going to give you an assignment right now.
Do we have mass?
I already know it's gonna happen.
Yeah,
What's the teacher?
Feel special.
One more, hold on.
Is it Inelastic?
Mad, like
Inelastic?
history. I tried history. I
Figure it out
can't get high on people like that at all. It is depressing. It does make my life. This is my perfect.
Just work on that one. 31. I'm going to probably have a worksheet for problems for you for the weekend tomorrow. I'll get you my Well, they're going down for sure, so it's a regular relationship, right? These are going up by 2. Down 250. Is that 1,500? Sorry. Down 750, down 2. Right. These are all half. Half?
Yeah, I got that in.
You have that voice.
You didn't hit my head.
Just really deep, that's all. Better than that, like 5-hour energy stuff.
2 is at 1500.
Where did they come from?
4 is at 750. It's exponential decay. Because it's going to slow down.
I know the feeling goes. I'm a parent, that's the point, go.
Why ask?
She wasn't.
Why can't you multiply?
Wow, Christian, wow.
So you're gonna have-
Oh my gosh. Oh my gosh. Yeah, she can look at me like that, okay?
Yeah, the why
Oh
was small,
my
like the
gosh.
difference is like quad is second.
Oh, I do love this
What's happening actually?
The differences are getting smaller every time. This is decay. Look, the difference between 750 and 250 is 500.
Just remember, I'm your
The difference between these is 125. The difference between these is 50. So the difference is getting smaller for the
So
line.
is it the difference is divided?
When the difference is getting smaller, it's decay. When the difference is getting larger, here, it's.
But like just generally, what would I use to figure out exponential?
What do you mean, what would you use?
Like how
Huh?
to find
Pick two
quad.
points.
All over me that one
Pick 2 of the
day.
points.
You know how like the quad,
That is
like all
like
the
a-
seconds, you find the difference between second numbers, like you would find the difference. So what is the exponential?
I don't know.
I didn't say anything all day.
You look, that was a long time ago. I'm trying to figure. I personally took a curve to it. I was looking for trying to put a curve on it.
What I do English today?
I showed you what it is.
We're being pessimistic.
You were being
What is it?
Hi, I got